from Geostatistics for seismic time to depth conversion. The objective is to have the map of the depth, the isoline of the depth, conditioned to the well data. Here we have the well data. I have 1, 2, 3, 4, 5, 6, 7, 8 wells. So at these points, the depth is known, and we are sure about the top formation depth. The other information that we have, they are the seismic horizons. Here you can see that here it is marked 1,200 milliseconds. So the seismic information are in the time units, and our certain data are in the meter. We call them hard data, and the soft data as auxiliary data. So again, it's a multivariate situation. We can do seismic well time and also incorporate the fault sticks if we have. And finally, calculating a spill point and volumetrics, these two are mostly related to the petroleum industry. Sometimes interesting for the other industries, especially the spill points, sometimes less. So you can see the hard data, that the green data, they are limited. They don't have a very good geographical coverage, but the seismic data have a very good geographical coverage. That we call them soft data. The idea is to use geostatistical mapping in order to interpolate the well markers that they are hard data, and at the areas where you don't have the data, like for example here. We have some auxiliary data, which is our data horizon. The methodology that I'm going to show is not co-kriging, is something related to universal kriging. As you know, in the universal kriging, or another name is called kriging with external drift, there is a very tiny difference between these two methodologies, external drift and also universal kriging. In one of them, the drift or the trend is inferred. In the other one, the drift or trend is not inferred, but is calculated by the user. But the main idea is the same. It means that we calculate a residual. The residual is between the marker values, Zi is the marker value, and the Mi. What is Mi? Mi here in the context of time to depth conversion is this value, which is converted by a regression, by velocity model to the depth. So we can call it an imprecise depth map. And you can argue that the velocity model itself has some sort of uncertainty, and we'll see what is the solution of geostatistics to include the uncertainty of the trend model. So because your trend model, we define a regression between the real value and the estimated value. For example, in the geothermals, you have the Z versus the temperature, and this temperature, instead of having the best or the average value, we can imagine that the standard deviation or the variance or the dispersion around the regression could be considered as the error of uncertainty of the trend. The options available in Isatis.neo are either we can apply univariate modeling of the top formations from top to bottom. This method is called layer cake, or like here, if top and bottom of horizon 1 are correlated, the same for the horizon 2, we can concatenate them and apply some sort of multivariate or co-kriging. And also we have some post-processing options if there is no rule, or if, for example, here the top formations are erosional, or if here they are unlapping. So it will apply some post-processing in order to generate the correct expected geometry of the tops. We can do interpolation of the depth directly, Or if we have some lateral velocity variation, we can apply our interpolation on the velocity, because once you have depth or velocity, you can have the other one. So having the depth, because the time is known everywhere, we can calculate the velocity q. Or if you have the velocity, if you interpolate the velocity, because we have the time, we can also calculate the depth. So there are these two options depending on the stationarity of your velocity in a lateral direction. And also the Bayesian approach, here is a Bayesian kriging, allows you to incorporate some sort of dispersion for your velocity model or for your trend model. So Bayesian kriging could be used in universal kriging or kriging with external drift if the regression between your auxiliary variable and the primary variable is has a high dispersion. The advantages of this tool, which is designed in the and also implemented in Isatis.neo Petroleum Edition, is that it's easy to apply, easy to learn. It includes all the necessary tools that you need for doing time depth conversion, and also it's some sort of automatic workflow. And user is not necessarily obliged to fill all the parameters, but you have the option of tuning the model. It can help you to generate the geometries that you expect if there are some disconformities, or if you have some unlapping, or if you want to permit the intersection of, for example, if the layer B is some sort of the water table which is built inside the reservoir, so it's possible to ignore the disconformity and the unlapping. The points that you can see here, they are the points which is called spill points. In fact, they are the points where the neighboring reservoirs are connected. And in Isatis.neo, there is some tools, some algorithm in order to find out these points. And because you can incorporate also the simulation, statistical simulations, we can imagine that we can have several surfaces, top surfaces, in order to have an uncertainty of the spill point. And if you have the fault sticks, the fault modeling could be done inside Isatis.neo, and the gross rock volume estimation could be done automatically at the end. Here is a top formation of an example that I will just show you the demo. And you can imagine what are these points. These points who are accumulated here. In fact, based on the different surfaces, 25 scenarios, here I generated 25 scenarios. For each scenario, there is one spill point. And these white points are the spill points, which are very important for the production planning. So if the spill points are concentrated in this area, it shows that very probably this point is a connection between our main reservoir and the neighboring reservoir. And also there are some possibilities in some other areas like here, or for example, in one realization, the spill point drops here. But in general, the main spill point is here, and with some other possibilities in other areas. If you are interested in time depth conversion, there is a free white paper that you can download it from the site of Geovariances. You can ask me if you need the link. And also recently we published or presented in the EAGE a pedagogical article for mapping groundwater level using universal kriging, and also some discussions about the choice of the neighborhood, where we can choose a neighborhood which is, for example, different from your background range. Should you really respect in 100% the recommendation, or what are the range or different suggestions for the good choice of the neighborhood? And finally, if you are interested, some of you have already participated in our trainings. There is one training about these applications, and the private training also is another choice. So let me do a quick demo inside Isatis.neo for the time depth conversion in the Petroleum Edition. Here are the markers of the different wells. The data set is a real data set, Equinor well field free data, which is available. You can download it, and like me, that I've imported the data, and also the faults. They are the faults that are modeled by the geoscientists in the Equinor. We could do this inside Isatis.neo, but I imported the official faults. They are the standard official faults on this field, and we wanted to have these surfaces. In fact, the surface of the top hooking, also the bottom, the base and the top. The tool could be found at this area, conversion and uncertainty. Here are the tools specific for Petroleum Edition: fault modeling, synthetic marker modeling, merge data, and mistime interpretation in the seismic and also in other geophysical methods. If you have some inlines and crosslines, and if the crosslines are not matching, it's a very nice tool that you can use based on geostatistics to correct your geophysical crosslines. I mean that when you have some crosslines and one inline, at these points, sometimes we have discrepancies. And these discrepancies could be And this discrepancy could be corrected based on a method called kriging with the measurement error. I don't go through the details, but since here the public is mostly geophysicists, it might be interesting for you. If you apply kriging on the results that have discrepancies at the crosses, the map will be very much noisy. But adding applying this method will in fact add some measurement error to those measurements who has high discrepancy, and lower measurement error to those who has a good compatibility between inline and crossline. So it will reduce the artifacts where we have higher difference between the crossline and the inline. So it's a tiny correction, just statistical correction, which is available in Isatis.neo. And what I want to promote now is time to depth conversion tool. If I open it here, you can see that several scenarios I have tested previously. Let us do the basic one. The basic one is using ordinary kriging by a monovariable tool in the layer cake method. Simply, the data are loaded. The markers, the faults, and the output grid. Here we have to specify the strata in a chronological order. We can see the different options that we have. If you want to do a layer cake, they should be interpolated separately. Here I wanted to do the first scenario for me is the basic one. I wanted to test the basic method, but it's possible to do co-kriging between them if you are sure that they are correlated. And the post-processing here I chose erosional. But if this is unlapping, if your geologists think that the post-processing should be something else, it's possible. And also the depth or the velocity, whether you want to calculate from the top SRD equal to 0, or whether you want to calculate it based on the previous horizon, it's possible. On the left, you can see the velocity models, which are calculated for different sets. For Shetland top, hooking top, and also hooking base. For the hooking top and base, the velocity is very similar. Still, we have some dispersion. So if you want to include this dispersion in your trend modeling, because it's very similar to universal kriging, it's possible to change the formula in order to add some parameters of the average and uncertainty in the or standard deviation in the equation of the drift, called Bayesian coefficients. And also here, instead of modeling velocity depth, you can model velocity with two different options that we have for velocity modeling. And if you use the Bayesian one, there is one two tools. In fact, one of them is run bootstrap, the other is run Bayesian prior. They are the algorithms that help you to find out the uncertainty parameters of the Bayesian trend modeling. Next, and in the next step, I chose to do variographical analysis automatically. Here, the variogram is done based on covariance, which is negation of variogram. And the results, if I want to show you quickly the results, make it bigger, the size. Yes. And also add my compass. I have the habit of using the compass to see everything in the right direction. So it's the top shed length, which is result of kriging, topography, and also base. So I can reduce the Z scale because I'm adding too much vertical exaggeration. It's the real scale. Or I can add, for example, 3 because a little bit have more variabilities or highlight the variabilities. This is the result of kriging, the best estimate, but here I have done also 25 simulations. So it's possible to visualize the simulations from the simulation. How can I move from kriging to simulation? It's here. It's a simulation number 1. So it's the first scenario. Second scenario, third scenario. As you can see, based on the parameters that I've chosen, we can have the different estimations. Globally, there are reservoir, which is here, is the same. And here you can see that it's a neighboring reservoir. And the split point that I talked is about here, but I will show you the split point analysis in the next step to find out the connection between the two adjacent reservoirs. So I have 25 different scenarios. And in the next step, here we can do some volumetric calculations. Let us do a preview. Here is our preview. And it's my preview. We add all these compass and everything. Perfect. The reservoir that I have is this one. And Z scale, I'm not sure whether it's good or not. I prefer 3 on this example, but even in Isatis.neo, we have by default 5. Something that I mistake. My mistake is that the top reservoir is not Shetland. Here is the top again. Because of that, my shape is not something that I expected. I preview again. Yes, now everything seems correct. Here is a reservoir, the main reservoir that I want to study. And the neighboring reservoir is one of them. He's here, the tiny reservoir like here. And let us run split point. It will calculate the probability of being a reservoir. And based on these probabilities, and the points you can see, it's not a very big data set. And also I have increased a little bit the size of the blocks for this presentation. So the probability of the being reservoir is here is 100%. Here is much less. And some probabilistic calculation will give us the reservoir volume at the bottom. It's calculating all the histograms, cumulative histograms. It's the histogram of the depth and also histogram of the volume. The volume is not available because I didn't complete all the parameters here. Now, if I show you the spill points, which are too big, yes. Here are the spill points that you can see. The majority are in this area. So it is my main reservoir under study in this case study. And here is one of the neighbor, the other neighbor, and we can see that the points are shown. It's possible also to change the view. This is the first scenario. This is the second scenario. So this spill point is for the scenario number 2, scenario number 1, scenario number 3, number 4 doesn't have it's very it's behind. Number 5, number 6, number 7, etc., etc. And all the spill points are available here. And the best estimate is kriging, of course, because the scenarios are equiprobable possibilities. And in the next step, it's simply some volumetrics. I think that my parameters are correct. So here is an oil one. And if I click on the run, it will calculate my best estimate and probabilistic and my best estimate. Why? Because here let me add some manually some sort of range in order to generate the volumetrics. Yes. Now we can see that the curves of, for example, the optimistic volumetric evaluation and the pessimistic one, which has a lower volume, the highest volume, lowest volume, and the average one. The uncertainty that I have chosen here, it will define the range of the volumetrics. So if I reduce the uncertainty here, for example, instead of changing from plus 30 to 5, from plus 5 to minus 5, we will have less range. Or if, for example, it's from plus 1 and minus 1, it will still be smaller. So that's all for this presentation, this tiny presentation that I wanted to show you quickly what is the time-depth conversion and the tools that we have in Isatis.neo. If you have any questions regarding this tool, we'll be happy to have your ideas and to accompany you or to assist you on your data.